Welcome to submodule 1.2. Today we'll be talking about the components of a quantum network. My name is Shanice, and today we'll cover what is a quantum network, as well as the different types of nodes that we distinguish within a quantum network, which are the processing nodes, photonic clients, hubs, links, and repeaters. So what is a quantum network? A quantum network is a collection of connected quantum resources. So we have different nodes that have some kind of quantum capability, and we connect them via links. Now, in a collaboration in Europe that is called the Quantum Internet Alliance, we are working on a large-scale quantum network, and there we envision a quantum network to be consisting of metropolitan hubs connected over longer distance links. And in such a metropolitan network, different types of end users are connected to a hub, and the different types of metropolitan networks are connected over long-distance backbones between the hubs. The first node that we'll talk about is a processing node, and this is the node that has the most quantum capabilities in a network. It is a full quantum computer, sometimes referred to as a server, and generally these depends a little bit on the different hardware that you use, but we generally expect these to have the ability to hold qubits, so have some kind of memory. We want them to be able to send qubits to do quantum communication. We want to be able to perform gates, to manipulate the states of the qubits, and we want them to perform measurements or a readout of qubits. Some different possibilities for how this can be realized in hardware is in trapped ion-based servers or different Collins senses in diamonds, such as nitrogen vacancy centers or tin vacancy centers. Can be superconductors or quantum dots or even photonic quantum processors. And depending on the type of hardware that you use, you will have different error models and slightly different capabilities. We distinguish a different type of end node called a photonic client. Note that in Q&E this is actually the same thing because they're all just nodes. But if you give them different abilities, we call them a little bit differently. So the photonic client is actually a scaled down version of the processing nodes. So it has less quantum capabilities and is therefore supposedly a lot cheaper. And these photonic clients can have the ability to either send qubits or receive qubits and measure them. This way we can in different kinds of applications, connect to other nodes and perform some quantum applications without needing to have the full quantum processors available to all of the users. Some interactions could be client-client interactions, but this is only possible if the client can send quantum information. And this is in applications such as QKD, which you will learn about later. And then there are other applications that require a client to connect to a processing node, such as blind quantum computing, which we'll also learn about later. So the next element is a hub, and all of the end nodes, being the processing nodes and the photonic clients, are connected to a hub in a metropolitan network. And this hub acts as a link between these end nodes. So these end nodes will request to the hub to be connected to each other. And then this hub will be a quantum resource sharer. So whatever these two end nodes will need to connect to each other will be at the hub. And if there's a lot of requests coming in from different end nodes, this hub will also act as a scheduler to say which node will be first to connect with the other ones and which will have to wait in a queue. So then, of course, in order to create a network, which is a collection of connected quantum resources, we need to connect them. And we connect them in different ways. The most common way in which we connect quantum resources is with optical fiber. And over which these optical fibers we can then use to send qubits, usually in the form of photons because they're very fast. However, this is a lot more difficult to do over larger distances. So if we have to cover a very large distance, we have to deal with exponential losses in fiber. And the problem with exponential losses in fiber is that the longer you have to send information, the more likely you are to lose it. And in quantum mechanics, we deal with the no cloning principle, meaning that we cannot arbitrarily copy a quantum state. Classically, how we deal with loss in fibers is with devices that copy the information that we're sending into a lot of copies and then sending them all at once, and then hoping that at least one of them arrives. Because we have a no cloning principle, we cannot do that with quantum states, so we have to come up with different ways of getting our information across. So over long distances, we can do that in two different ways. We can use satellites, or we can use quantum repeaters. Now, in QNE, satellites are not modeled, so this is not an option to look at yet in the QNE platform, but you can give quantum nodes in QNE the ability to be repeaters. And these repeaters, they take long distance links and chop them up in smaller pieces, such that we can create entanglement in all of the smaller pieces separately, and then connect them into a longer link at the end. So to summarize, the components of our quantum networks are processing nodes and clients that in metropolitan networks are connected to a hub, and then they are connected through quantum links in the form of optical fiber, and to cover larger distances, we use repeaters.